Hello, friends. Today we're going over the last unit. Again, in the way that we structure units in the course that I teach. Unit 6 includes simple harmonic motion and gravity. So we'll start with simple harmonic motion. The very basic information, omega equals 2 pi over t, where capital T is the period, omega is the angular frequency. Not necessarily angular velocity, but it can mean angular frequency, right? Like how many angles there are per second that go by. Frequency, don't forget, is 1 over the period. Omega then is also equal to 2 pi f, 2 pi times the frequency. The basic equation here is a cosine omega t plus phi. So omega, angular frequency, if you multiply that by time, that gives you a particular angle. And then, a times cosine of that will give you a certain amplitude, kind of where you are. And it creates a wave, a function. Phi, that's the phase angle, right? So that's shifting it left or right. Remember, if you have a transformation in the function, that transforms it horizontally. If you have a transformation outside the function, like the a, that transforms it vertically. So here, by having a, that's the amplitude that's stretching it. And we never see a midline shift here. We never take the whole thing in, or rarely, I would say. In for the velocity. So again, the velocity equation, what happens oftentimes in students in AP Physics 1, they learn these and they memorize 3 different equations, and they have to memorize like, oh, the velocity is this, the acceleration is that. Here, you memorize one equation, this, and then the velocity equation is just the derivative, the time derivative of this, right? So if you do dx dt, this is what you get. And then you take the derivative again, and you get the acceleration equation. And so notice we're back to the same thing, except that it's, negative omega squared times the same equation that you had. Maximum velocity would be a omega. So it would be the absolute value of this coefficient in the front. The maximum acceleration would be omega squared times a. I didn't write that down, but maybe I should. So a max is a omega squared. And what we're really concerned with there, if we're looking at the max velocity or the max acceleration, is the magnitude of them. Right? Notice I didn't put arrows above them. In terms of the graph, this is what it looks like. Right? So the cosine graph starts at the amplitude, and then it goes to zero, minimum, zero, amplitude again, right? Or you got positive and negative amplitude, you could say. The derivative of that, right? So the velocity graph looks like this. You can see how they're related to each other. And the acceleration graph is just the velocity graph flipped. Those squiggles shouldn't be there. It's just bad handwriting, drawing this quickly. Okay, other equations. If we take other things we know, now we're just like pulling things together. This is often what we do in physics. We introduce some new concept, and then it's like, hey, everyone else, you're invited to the party. And we just apply everything else we know. So using the kinetic energy, if it's 1/2 mv squared, well, we have a function for v, don't we? So it's 1/2 k a squared, and then this whole thing. So it's just the square of the whole velocity function. So there's a function for what the kinetic energy is. For the potential energy, depending on what it is, like, so this would be for a spring, right? 1/2 kx squared, a Hookean spring. Then we take the position function and we square that. So we get E total then would be 1/2 Ka squared. So in other words, if you take this is the amplitude. This would also represent then the total amount of energy if you have a spring oscillating back and forth. Also for a spring, another kind of handy equation for the velocity is plus or minus omega square root of a squared minus x squared. And there's a derivation for that, and it's in the original video, the lectures, right? So all of my lectures, the whole course is available on my channel, so you can go back and watch every lecture from mechanics if you so desired. You could do that. And in a spring, also omega equals the square root of k over m, right? So, and don't forget omega is 2 pi f. So if we solve for f, then we get 1 over square root of k over m. What I often do, I don't know why, but for some reason in my head, I can't keep straight. Like, oh, is it k over m or m over k? Just think about the units, okay? In k, you've got, it's basically kilograms per second squared. It's a weird thing. But if you were to simplify all the things that are in k, it's kilograms per second squared. And So if you've got kilograms per second squared, you know frequency is 1/seconds. A hertz is 1 per second. So then you think, well, how do I have to arrange K and M in order to get 1 per second, right? So the kilograms cancel out with the meter, the mass on the bottom. I have 1/second squared. Square root of that is just 1/seconds, and that's frequency, right? So you don't have to necessarily memorize which one's K over M, but then you just have to go through the work. It's real quick. Use the units. Use the units to check your work to help you solve questions. Again, I've survived whole parts of my physics education just by paying attention to units and thinking about what the quantities were and what I wanted them to be. Okay, continuing then, pendulums. That's the other big thing with simple harmonic motion. You've got pendulums and you've got springs. A lot of the pendulum equations depend on what's called the small angle theorem. And I have seen it in some of the grading guidelines that you're supposed to cite the small angle theorem. And that's the idea that at small angles, sine of theta is about theta, right? So less than 15 degrees. So when you're giving an answer, you can say something like, assuming the small angle theorem, blah, blah, just to mention it would be enough. So anytime you see a pendulum question, not a bad idea to mention the small angle theorem. In this case then, right, so if you've got a pendulum swinging back and forth, S is sort of the arc that it cuts out, and X is the linear distance from one point to the next. For small angles, X is about S. It means the tangential velocity, dx over dt, is about ds dt. And then same thing for tangential acceleration. dA over dt is, the second derivative of the this arc velocity, or the arc position, I should say, function, if you have that. Omega, root g over L. Again, to remember the units here, I think like omega, well, what is that, right? It's radians per second. So what do you have to do with g and L? G is the acceleration due to gravity, right? Meters per second squared. What do you have to do with this to get 1/seconds on the bottom, right? Your seconds on the bottom. This also has equivalent forms. F equals 1/2 pi root g over L, or T equals 2 pi L over G. This is the leg equation. Pi looks like it has legs, right? It looks like two legs. And LG like leg, right? So the legs there. So T equals 2 pi over square root L over G. That is, if you need something to help you remember that. A physical pendulum, that's when you have a solid body that's swinging back and forth. So something like a meter stick, or if you took like a wheel and you hung it up and the whole wheel was swinging back and forth. Regular pendulums like these things, that's really a point mass at the end of an ideal string. For a physical pendulum, there are a couple of equations, and it involves the moment of inertia. I call this the damage equation because you got dmg over I. So omega equals the square root of dmg over I. T equals 2 pi square root of I over dmg. The I that you're looking at here has to do with the moment of inertia about the axis of rotation. So you got to do some math to figure that out. Go back to the other unit to work with that one. Damped oscillation. So as things are oscillating back and forth, a spring or a pendulum, eventually everything slows down, and so that looks like this, right? Over time, it decreases. So the amplitude is decreasing according to negative bt over 2m, but the omega is also decreasing. And omega prime, or no, sorry, it's not decreasing. Omega, it's a different omega because you've got like forces involved there. And this is omega prime. It's not the first derivative. This is what it looks like. Square root of k over m minus b squared over 4m squared. You're probably not going to have this memorized for the AP test, but it's good to know that this is a different expression here that goes in there for that. Energy then, the total energy decreases according to e to the negative bt over m. You get used to seeing this. You see this a lot. This form of an equation, even in E and M, we get this kind of thing showing up. All right, so for gravitation now, moving on to the next chapter, this might be another unit, or I think actually in the new curriculum, the way they split up, College Board split it up, this is mixed into some other units. Basic equation, gravitational force Gm1 m2 over r squared, and G is 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. I think they give this to you, but not bad just to know offhand. If we're going to find the force, the gravitational force, from like a large extended body, then what we have to do is to find the force from each individual piece of it and then add them up, right? So we have to add up all the little individual forces. And so that would be gm over r squared. So this is actually the gravitational field times each little piece of the mass that we're adding up. And so you could do a derivation for a gravitational field that way. And again, in the lectures, I go through a derivation or two, and you can see that. Field, okay, electric field. Think of not electric field. I was just talking about that. Gravitational field. It is a ratio, right? So you go to the grocery store and you buy meat, and it's like $4 a pound. But when you go out, you're not paying $4. You're paying $4 times however many pounds of the meat that you're getting. Same thing here. Field is how much force there would be for every 1 unit of charge. It is a ratio. Fields are ratios. It's the force per unit mass, and this is the way that we calculate it. Little g equals gm over r squared. It also happens to be equivalent to the acceleration in this case, right? Because if you take the force and divide by the mass, then you get acceleration, and that's also what we get here. It works with gravity. Electric field is not the same as acceleration because there you're finding force per coulomb, force per charge, not force per mass. Okay, inside a solid sphere, though, so there are some different geometries here. If you're inside a solid sphere, the equation for the electric field looks like this. It's gm over big R cubed. Big R is the fixed radius. This is not a variable. This is the radius of whatever object it is you're talking about, times R. R is the variable as you go farther out. So this is basically linear, right? It's a linear function because as R changes, it's just R to the first power. Potential energy, so gravitational potential energy, UG equals negative gm1 m2 over r. Looks the same as force equation, except it's negative and r is not squared. This is measured in joules, just like everything else. Here's an example of the potential energy of a system of three objects, where it would be negative g. Just you're finding all the relationships of the potential energy and you're just adding them up. It's not a vector. You can just add everything. Escape velocity. Okay, if you were to fire something off from the surface of a planet, at what velocity would it have to be to reach all the way to get to infinity, right? To get so that it reaches zero kinetic energy at infinity, or when the potential energy is zero. Again, I go through the derivation for this in the original lectures, but the escape velocity is radical 2 gamer. That's gm over r, so I call that the gamer. We see that other places as well, but square root of 2 gm over r. Kepler's laws. First law, planets move in ellipses. Second law, planets sweep out equal areas in equal time. What that means is they're traveling faster when they're close, slower when they're farther away. The key idea here, in terms of the cause of that, is, or you could think of it this way, as conservation of momentum. If you're looking at a problem and there's a satellite and it's close at one point, slow at another point, how do you find, if you know the velocity and the radius of one, how do you find the velocity at the other? You're thinking conservation of momentum for that. Okay, and then Kepler's third law, that the square of the period is proportional to the cube of the semi-major axis. It was a mouthful, but basically it means, right, so t squared is proportional to a cubed. A is the semi-major axis. Like, the concept here is simply that when you've got different objects going around the same source object, like different planets around the sun, the ratio of t squared over a cubed is the same for all of those planets. The closer a planet is, the shorter its period of orbit. The farther away it is, the longer its period of orbit. The orbital speed of a single satellite is v equals radical gamer, square root of gm over r. And finding eccentricity, this is a pretty rare thing to show up, but not a bad thing to know anyway. Eccentricity is 1 minus rp. So rp is the perihelion, divided by a. And I have a here, but I'm thinking actually that this should be RA now that I'm looking at it, because if it was just RP over A, then that would mean, so when you have a circle, the eccentricity is 0, right? And so that would mean that RP is equal to RA. The perihelion and the aphelion are the same, right? Or, oh no, sorry, RP over the semi-major axis. So A is the semi-major. Semi-major axis is half of this whole thing. So when RP is equal to A, right? When RP is equal to this, the semi-major axis. So if it's a circle, this is right in the middle. And so this is half of that whole distance. Then this is equal to 1. 1 minus 1 is 0. Have an eccentricity of a circle then is 0. You can think lower eccentricity, more circular, higher eccentricity with a limit of 1, right? Then the more stretched out it is. The kinetic energy of an orbiting object is gmm over 2r. And so here's a function or a graph of the energy of an orbiting object. The kinetic energy and the total energy and the gravitational potential energy. So the magnitude of the kinetic energy is half the gravitational potential energy. So when you add those together, then you get half the magnitude of the gravitational potential energy, but on the negative side, right? So E total is 1/2 UG, and K, the magnitude of K, is 1/2 of UG also. That's what that graph looks like. Those are the major concepts to review from the last unit of AP Physics C mechanics. Check out the other content on my channel. If there are any particular things you want to review, the whole course is there. So don't forget to like and subscribe. Good luck on the test.